Hello, and welcome back to another video where we're talking about KOS in Kerbal Space Program, working on our getting longer script that is going to get us to the moon. And today is all about refactoring. Refactoring is when you work with some code that already works in an effort to make it better. And I have a laundry list of to-dos here that I want to focus on in this episode. So this one's going to be a little bit different because the goal is by the end of this is that our code should just work as well as it did before, but there's a very specific reason why we are doing this. If we look at our main function, we have do launch, do ascent, do auto staging until we get to the right apoapsis, do shutdown, and do circularization. And that all works. We ended up circularized. And, well, what's left? Well, we have to do another maneuver to transfer us to the moon. Depending on how we do that, we either are going to slam into the moon or we need to circularize around the moon. It's kind of up to us to decide what we want to do, and then we have to do some sort of landing maneuver. So there are really only two more kind of higher level functions that we're going to be writing, but the next one, transferring to the moon, is actually pretty similar to the way that we've done our circularization. And that's the reason that we did this circularization in this convoluted way of creating these improver functions and creating this big execute maneuver function, because then we can use it to execute any maneuver. And we can use this improver function to improve any maneuver. Now, of course, right as I say that, that's not actually true. That's a lie. Our improver function right now uses this score function. It's going to pass in the data to this score function to try and come up with a better set of variables to use to create a maneuver. And this score function returns a result that's based on the eccentricity of the orbit, because we wanted a circular orbit to circularize around Kerbin. And that's great, but it does mean that anytime we try and improve any maneuver, maybe the goal isn't for us to be circular. Maybe we're trying to get to the moon, which is most assuredly not a circular orbit. Well, we need to pass in some sort of way to say, don't score it based on eccentricity, score it based on some other criteria. But in order to do that, we need to clean up a bunch of things. So first off, at the very end of the last episode, we ran into an issue where we forgot to unlock the steering. And I just put it down here at the very end, which was sort of fine. But actually what I want to do is I want to put this where it belongs. The reason that we ended up with an error is because in our execute maneuver function, we locked the steering at a maneuver target, and then we throttle up, we throttle down, and then we remove the maneuver. So the way that lock steering works, if we go down to the body of lock steering at maneuver target, lock steering to MNV burn vector. That means every time that KOS is trying to say, hey, what should I be pointing at? It's going to look at this maneuver, and it's going to say, hey, point at that burn vector, which is going to compute multiple times. But what happens when we remove this maneuver? Well, then there is no burn vector, and so it goes, hey, I don't know what I should be steering at, and it throws an error and it dies. So what we need to do is make sure that we say, hey, let's unlock the steering at the end here before we remove the maneuver, because we're saying, hey, just destroy all of that data, and then when we're trying to point at it, well, there's nothing to be pointing at. So we'll put the unlock steering here. And then that should fix our problem, and we can take it out of this main loop. Wait until false we're going to keep in here just because it keeps our program from dying, which is nice for the moment. Next thing, and this was pointed out to me in a prior video by Don Baradu, is that when we did our maneuver time calculations, we were assuming that every engine was not thrust limited. If you go through when you're creating your craft, you can thrust limit the engines, and that's a valid thing to do. What we are doing is we were looking at the max thrust in calculating the maneuver burn time. We're looking at the max thrust compared to the ship's max thrust, and that's not actually what we want to be doing. We want to be looking at the available thrust. If we look at the KOS docs, in vessel, there is a suffix that is available thrust, and it says the sum of the active limited maximum thrust compared to max thrust, which is the sum of the active maximum thrusts. So that's a little bit confusing, but if we have an engine thrust limited to 50%, well, then if we pull it at full throttle, it's going to only be giving us 50% of its thrust. So we need to factor that in if we want to make sure that this function can be reused in multiple circumstances. And if we click over to engine, we're going to notice the same thing. There is available thrust at full throttle accounting for thrust limiter, compared with max thrust, which is the untweaked thrust limit. So we don't want to be using max thrust, we want to be using available thrust. Let's refactor our code to do that. And this is actually pretty easy. I'm just going to go ahead and look for max thrust. And can I replace these? I don't know. Can I replace? I don't know. Replace all of these. Change all occurrences. Control F2 is how you would do that. But available thrust. Great. One more cleanup off of our list. Next, make our improver work with lists of any size. So we spent a fair amount of time being kind of ridiculous in terms of determining our improvement candidates. So the way that we represented a maneuver was as a list of values. So 1, 2, 3. And we said, hey, the possible improvements for this would be list 2, 2, 3, or maybe list 0, 2, 3, or maybe list 1, 3, 3, or maybe list 1, 1, 3, etc., etc. You get the idea. That we tried tweaking each of these values +1 or -1 in each direction. And to do that, well, we just copied and pasted all these. We said +1 or -1, +1 or -1, and we just wrote all of these out. And of course, we had an even more complicated version that this got reduced down to. What I'd like to do is see if we can find a clean way to generate this list of candidates in code. So we're going to go through and replicate this whole local candidates as list thing that's automatically generating all this stuff. The way I'm going to do this, we're going to start with an empty list of candidates, and we're going to say until index is greater than or equal to data length. So we're going to loop over this for all of the elements in this list. Now I've got an example here of A, B, C, D. Our list is a couple of different values. We need to set the index to an initial value, and then inside here we'll say, hey, set index to index +1. So then each time this loops, this index value will be increased by 1. So first we're going to be referring to A, then we'll refer to B, then C, then D. What we're going to do is we're going to say local increment, which is what we're going to call, we need to add 2 items to this list of candidates, the +1 and the -1. Let's see, inc candidate is, what we're going to do is we're going to take data and then just copy it. We will copy the data list. This is going to create a new list, but with all the same values. And we'll say local dec candidate, which is the decrement candidate, is data copy as well. Now all we have to do is modify the value at that index. So the first time we loop through this, we're going to say, hey, let's take A and add 1 to it inside increment candidate. And inside decrement candidate, we'll just subtract 1. So we'll say set inc candidate index to inc candidate index +1. We'll do the reverse for dec candidate -1, and then we'll say candidates add inc candidate and candidates add dec candidate. Cool. So this refactor should work just fine. Now we'll have a list of all of these candidates. If we think about how this works initially when we loop over, we're going to say, okay, cool. Inc candidate is a copy of this list A, B, C, D. Then we're going to say, hey, take the 0th element, which is going to be A. We'll say, instead, set it to A +1, and then add that to our list of possible improvements. We'll take the dec candidate. We'll say, hey, try A -1, and we'll add that to our list of possible improvements. And then we'll just go to the next one. We set the index to index +1. So then we do the same thing for B, the same thing for C, the same thing for D. Now, on the face of it, this doesn't look like it's saving a lot of code. Shame on us, I guess. But in fact, it does, because if we were to add more elements to this, well, then this loop is just going to run more times. We don't need to add more code to make that work. So that's one cleanup that we can be somewhat proud of. It is one option of how we could do this. There are some other strategies we could use, but this will work just fine. Okay, let's look at our next item on our list. Okay, make our improver work with a list of any size. Cool, that works. Make the maneuvers converge faster. Okay, so this is going back to what we just did. Improve is going to do this whole +1 business. And that's fine, but it means that it's going to be really slow. What if instead of improving by 1, we improved by 100? Well, that's going to mean we try a maneuver and then we say, hey, is it better to try and do it 100 meters a second more in the prograde direction or 100 meters per second less? It means that we're not going to find stuff in the middle there. So we can increase the size and it'll make faster adjustments, but it's not going to be as precise. So instead of using this number here, what I'm going to do is I'm going to say, hey, let's actually have this be something we can pass in. We'll say step size. How big of steps do we want to be taking when we're trying to make these improvements? And we'll accept that as another parameter to improve. So where are we calling improve? Well, we're calling it in our do circularization. We can go ahead and say, hey, we've got this loop that does this improvement step. Instead, we'll pass in 1, and this would be equivalent to what we were doing before. What we can do is say, hey, let's try improving it with 100 steps of 100 wide, and then we can try doing it again after we found the best thing using very large steps with, we'll do another loop, just improving this maneuver in steps of 10. And then do another thing, improving this maneuver in steps of 1. Well, that seems fine to me. That seems like a reasonable way of slowly getting more precise. So first we try very wild strategies, and then as we get to the best we can using a blunt tool, we start to use a more precise tool until we're eventually just saying, hey, is it better to be a second later or a second earlier and whatever? We're going to spend less time trying to find, with our circularization, it's going to take less time for us to find the right time to execute because we'll be making larger steps faster. Okay, but of course this isn't really do circularization stuff. This is kind of a whole big strategy, and this could use some refactoring too. So let's see. Let's try for step size in list of step sizes, 110, 1. Oops. And then let's see. Yeah. So we have a list of 110 and 1, and we do that. And then instead of putting in this 100, we can say step size. Then this all gets indented. Well, now we don't have to copy and paste this multiple times, for one. We've got now the same thing. We're just going to do the same thing over and over and over until we get the best value. So make maneuvers converge faster. That should now be done too. We haven't run any of this. We're going to have to jump in at the very end and see, hey, what fails? But that's kind of the joy of programming, right? I mean, in theory, we kind of ought to go through and test stuff over and over and over again, but it's also kind of slow. So we're gonna let this one slide. Functions using functions. Now, up until now, we've been using this function keyword. I've said function main and then these brackets. But little known fact, you can actually use these brackets kind of independently. And we're going to need to do that if we want to optimize a maneuver node for a different score, because our improver knows about this score function. And that's a bit of a problem because this score function is specific to the eccentricity. Okay. So what we want to do is actually, instead of just passing the step size to improve, we want to also pass how do you figure out what an improvement is? We want to pass the score function in. We want to tell it, here's how you know, not just have this function know, hey, this is what constitutes the best possible maneuver. The improvement doesn't even really know that it's a maneuver. It just knows, hey, you gave me a list. I'm creating candidate better lists, and you tell me what the best list is. The first thing I'm going to do is I'm going to take score, and I'm going to change all occurrences to, let's call it eccentricity score, and save that. And that should make this a little more obvious. Well, now our improver function looks dumb because it's just trying to find something that's not very eccentric. It's not trying to come up with the best list. It's not really scoring things. The score name was a little more generic than maybe it warranted. So the next thing that we're going to do is actually not use this eccentricity score at all. We're going to say, I'm going to have some sort of score function that's going to be passed in to this improve function. We're giving a function another function. We're saying, hey, improve this, and here is the way that you determine whether you've made an improvement. We're passing in a score function. Then we can go ahead and call a score function. This is a little bit non-intuitive because it's not looking for some global thing named score function. It's finding it because we're passing it in. So we need to look to where we're passing in a score function and say, hey, we need to actually give you that thing. Now, if we just say eccentricity score like this, it's actually going to try and run eccentricity score. It's not going to say, hey, here's the function. It's going to try and run it, and that's going to be a problem. We need to use this @ sign, and then we say, hey, here's how I want you to improve it by using this function that I'm telling you about. Then improver can go through. Now improver doesn't know anything about maneuvers. It doesn't know anything about lists. It's just saying, hey, you gave me a list and you gave me a step size in ways to change it. Then you gave me a way to determine whether the improvement is whether it's a better list. And then I'm just going to give you the best list that I can find. That's pretty neat. But we're not entirely done, because now I do want to go through and take this stuff out of the do circularization, because this whole idea of converging on the improvement, it's not really having to do with circularization. That should be its own sort of function. So I'm going to put this down here kind of near improver. I'm going to call this improve converge. Let's see, converge. I don't know, convert. I don't know. Sure, improve converge. And now this is going to take all of this big 4-step size junk. Say, hey, this is how we find the best thing. Now, this function needs to know about all these values. What are the things that we're missing here? Old score is eccentricity score. Well, now the eccentricity score is baked into here, but this improved converge is supposed to kind of be just a general function. So we need to pass in that function, the score function. And then we'll say, yeah, just call the score function. And call the score function, pass on the score function. In this case, we don't need to dereference it. And here we need to use the score function as well. And this I will freely admit this can be a little bit confusing, but it's going to end up meaning things are a little cleaner, which I like. Okay, what else are we missing? Improve is okay. Circ, the name is kind of weird. What do we want to do? Well, we want to pass it to, well, of course, we paste this stuff out. So improve converge, we're going to have to figure out what we're passing in. We're saying pass in this maneuver, and we're going to tell it how. And that was the eccentricity score. Eccentricity score there. And now we're saying, hey, okay, so improve converge, circ, blah. We're going to set circ to that, to the return value of that. And now inside here, this improved converge also doesn't have anything, doesn't know it's a maneuver. All it knows is that it's getting some sort of list. So some data and a score function. It's saying, hey, here's the list. Here's a way to make it better. Figure out the best possible thing using your convergent strategy of awesomeness. Cool. So then we replace these instances of circ with data, set data to the improved version of data. And then we'll break at the very end. And then at the very end here, we need to return the new data. So this improved converge function does all of this logic of looping over and trying this improvements and trying to score things. All we have to do now at this high level of what is a circularization maneuver, well, it says, hey, here's this initial list that we're thinking about, and go ahead and improve this as best as you can using eccentricity score as your metric, and then go ahead and execute it. So we can check this off of our list too. Functions using functions. This is a really interesting way of writing code, because it means that we can deal with some of the details of how we do things and keep them separate from what we're actually doing. Now, the reason that this is going to be helpful is because in the next episode, we're going to do something like do transfer. And what we can do is we can write that pretty much right now. We can say do transfer, and it's going to be really easy. It's going to be something similar to this. We're going to say, hey, local transfer is some list, and we may give it a different starting seconds because we're going to assume it's not 30 seconds from now. I don't know, or maybe not. And then we'll say transfer to improve converge transfer, but then we're not going to say eccentricity score because we're not looking for a maneuver that is low in eccentricity, that is circular. We're looking for something that maybe transfers to moon. That's easy enough. And then all we have to worry about is writing a function like this. Well, let's call it moon transfer score. And do that. Moon transfer score. And then our do transfer is done too. A whole process is reduced down to these 3 lines. We'll say, hey, here's some starting values. Go ahead and improve this. And then we're good. And in fact, we could combine these down to 2 lines if we really wanted to. We could go ahead and just say, well, single line actually. Execute maneuver. The improved converge of this value based on this score. Now, I don't like that. I think that's a little less clean, but we could do it. We're not having to modify these values anymore. We're just saying, hey, yeah, just make it the best possible thing according to this technique. And all we have to worry about when we're writing moon transfer score is, hey, given a list of data, is that something that would be a good maneuver for us or not? And then we return a score that tells it how much of an error it has. So that stuff we'll have to write in the next episode. But until then, I think we're in pretty good shape. So I hope this was helpful. We'll go ahead and comment that out as well. We'll tackle that in the next episode because we've got to figure out, hey, how do we determine what an error is when looking at a maneuver that's supposed to transfer to the moon? What is the error code that we should be giving it? And we'll worry about that soon. Next, it's time for us to fire up KSB and hope that this all still runs just fine. It's possible that we'll have a couple errors. We'll see. All right, and we're at least able to get off the launch pad. Now we are, in addition to seeing if there's anything broken, hopefully our maneuver should converge faster too. So I'm going to keep an eye on the apoapsis out here. I'm just using Flight Engineer to be lazy about it. This thing seems to be running just fine. Fingers crossed. We'll see if we can make it all the way up and haven't broken anything. Once our apoapsis gets up to 100,000, then it should try and find that maneuver, and I'm going to drop us out of time warp because it should happen a heck of a lot faster. Remember that we are taking these in step sizes of 100 and then 10 and then 1. So I'm slowing us down here, and we should hopefully see some maneuvers cropping up as soon as we get there. Shutting off, and look at that. It's done. So it took a little bit of time. Oh, now, of course, that's interesting. It found a maneuver. We don't have anything that's penalizing it for ending up in an eccentric orbit. That's amusing. But yeah, it ended up in an interesting place because our score is just based on eccentricity. So it's going to end up spending a lot more fuel than it needs to and ending up in a wildly crazy orbit. So that implies one last little adjustment that we can actually make. Because our circularization maneuver, we said, hey, go ahead and tweak these times and values and etc. But because our improved Converge doesn't care about what we're passing it in, I'm going to try something different. What about we just pass in time and delta V? Now, the only thing that's going to explode if we were to do that is this eccentricity score, because our eccentricity score is expecting us to pass 4 values, but we can change that. The fact that we're improving it, it doesn't care how long our list is. We rewrote it so that it doesn't care how long our list is. So let's instead say our eccentricity score is going to take in data. It's going to use the first for the times. It's going to use the second for actually, the second is going to be 0. And then 0, because these are normal and radial. And then it'll use data 1 as the amount in the prograde direction. So now all we're going to do is we're going to optimize a list of 2 values, and we're going to say, hey, this improver doesn't care what list you're passing it or even how it gets improved. It cares about the length of it, and the scorer is the only thing that has to care about what the list is actually doing, because the scorer needs to know, hey, is this a good way of doing it? We're just going to create this node, assuming that we have no radial and no normal delta V. So now all we're going to do is we're going to be tweaking the time and the prograde delta V. Let's try this. And this is flying once again. And of course, one other thing that we could have done would be to take our score and weight it differently so that it had some sort of penalty error score for an orbit that was eccentric. But really what this helped illustrate is that we were optimizing on some stuff that we didn't care about. We don't need to be worrying about those values even though they are part of a maneuver. The only reason we were passing them along initially was because, well, they were the only things we knew how to do, and because they would eventually be necessary for looking at other maneuvers. But now we can just pass in an arbitrary list of things, and that's pretty neat. We can optimize any sort of data. It doesn't even have to be maneuvers. And now if we watch this, oh no. Oh, of course. The problem wasn't that we ended up with a bad result. The problem was then we said to execute it, and of course execute is now a list of just 2 things. So we'll pass it a new list of circ 0, 0, 0, and circ 1. We need to unpack it in both locations, not just when we're scoring it, but also when we try and run it, because we can't create a maneuver based off of just 2 values. All right, we are approaching the 100 kilometer. At which point it should try its circularization. Now I've got no time warp on, and there we go. It has found the perfect maneuver, tweaking only the time and the prograde delta V value. 99,449 100,416. That's pretty darn accurate. And we know that if it were to tweak by 1 second in either direction, it would end up with something that was slightly less eccentric. Now, of course, if we just go ahead and let this thing warp ahead, we can verify that we haven't broken anything. I gotta get out of physical time warp, don't I? Yeah, because we're not even out of the atmosphere yet, and we have a plan. Nonetheless, let's see how. All right, we're getting there. Now we can warp ahead. All right, it's in 35 seconds. The estimated burn is 13 seconds. Well, at least we assume that's the case. No, yeah, 12.3 seconds according to Flight Engineer, which is a little more accurate. And now we're not wasting extra fuel on crazy normal or radial issues. Now, presumably that wasn't an issue when we were taking these steps by one because it didn't offer enough of an improvement. But you end up with something slightly more eccentric when we dealt 100 meters a second in some direction, or 10, I don't know. Whatever it ended up improving. Go ahead and execute that maneuver. And that was a heck of a lot faster than last time. Not only that, now we have some libraries that we can reuse in a whole bunch of different locations. So it ran, we got no error, we've unlocked the steering, and of course if I click in here then the camera's gonna go a little wobbly, but we are in a much better place now. I hope this has been, if not necessarily the most entertaining, at least somewhat enlightening, and we will make our way off to the moon in the next episode, and we can do it pretty darn easily, because we've got an optimizer. All we have to do is figure out, well, how to determine whether a maneuver goes to the moon or not. So we'll tackle that soon. I'll see you then. Cheers.